Okay, let's dive right into this explainer and demystify the mathematics behind measuring how data actually spreads out. Because, let's be honest, if you've ever looked at a simple average and thought, wait a minute, that kind of doesn't tell the whole story, well, you're absolutely right. Today, we're breaking down a brilliant statistical tool from our source material called mean deviation, or average deviation, and this is exactly what's going to help us capture the true shape of our data. We've got a really clear roadmap for our lesson today. We're covering the meaning of dispersion, meaning mean deviation, unlocking the magic of the absolute value rule, applying it to individual series, and finally, conquering frequency data with a simple four-step guide. All right, Section 1, Meaning of Dispersion, Understanding the Spread. Before we start calculating anything at all, we really need to understand the fundamental problem we're trying to solve here. So the big takeaway is that dispersion tells us how far our data points scatter away from the center. It gives us the true story behind a basic average. Just imagine two groups of students who both averages 75% on a test. In Group A, literally everyone scored exactly 75. But in Group B, half the class scored a 50 and the other half scored a perfect 100. The averages are completely identical, right? But the reality of those two classrooms is completely different. Dispersion is just the mathematical way we measure that exact difference, how much those numbers disperse from each other or from that central average. Moving on to Section 2, Mean Deviation, Distance from the Center. Let's see how our main tool for today builds on this whole idea of measuring distance from a central point. Now, what's really interesting here is that we actually have two distinct starting points to measure our distances, the traditional mean or the middle point, median. Our source material highlights formulas for both, and they're both great. If we choose to measure from the mean, our deviation is just our individual data point, x, minus the mean, which we represent with an x with a bar over it, x bar. But hey, if our data has some extreme outliers that kind of warp the mean, we might actually choose the median instead. In that case, our deviation is just x minus m, the median. Both are perfectly valid starting lines for our calculations. Section 3, the absolute value rule, the magic trick. You see, when we calculate distances, we immediately run into a major mathematical headache with negative numbers. Which brings us to a really clever statistical workaround. By placing our deviations inside absolute value bars, we are intentionally ignoring any plus or minus signs. Why? So opposite distances don't just cancel each other out to 0. Think about it. If your average is 10 and you have one data point at 5 and another at 15, the first deviation is -5, the second is +5. If you just add those together, you get 0. It makes it look like there's no dispersion at all, which is, well, a complete lie. And this brilliantly illustrates why we use those straight vertical bars, the absolute value. They turn that -5 into a +5. We literally only care about the pure distance, totally ignoring the direction. Section 4, Individual Series, the basics. Let's ease into the math with the absolute most straightforward scenario we have, calculating mean deviation for an individual series. Okay, here are the building blocks of our formula. Think of this as a simple legend to decode that intimidating wall of math symbols. X is just your individual observation, the raw number in your data set. X bar is your mean. M is your median. That lowercase d is the deviation distance we were just talking about. And n is simply the total number of observations you're looking at. Keep this legend in your back pocket because it basically unlocks everything we're about to do. For an individual series, the formula is honestly wonderfully simple. You just add up all your absolute deviations and divide by the total number of observations. See that Greek letter sigma? It just means the sum of. So you take the absolute distance of every single data point from your center, add all those pure distances together to get sigma absolute d, and then you just divide by n, the total number of items. You are quite literally just finding the average of the distances. It's elegant, it's simple, and it immediately tells you, on average, how far each data point wanders away from the center. All right, Section 5, the four-step guide, Tackling Frequency Series. Now we're going to level up to discrete and continuous series, which is basically just when data points happen multiple times. So when frequencies represented by that little letter f get involved, our formula expands a bit because we have to multiply each deviation by how often it actually occurs. Instead of dividing by just n, we now divide by sigma f, which is the sum of all your frequencies. Make sense? If the data point 10 has a deviation of 3, and it shows up in our data 5 separate times, we obviously don't want to calculate that same deviation 5 individual times. We just take that deviation of 3, multiply it by the frequency of 5, and boom, we get 15. That is exactly what the f times absolute d in the top part of our fraction is doing. If you just follow this strict 4-step masterclass, you are going to perfectly calculate mean deviation every single time. Step 1. Find your center line, either the mean or the median. Step 2. Figure out how far each individual data point, your x, sits from that center line, making absolutely sure to strip away any negative signs using your absolute values. Step 3. Multiply those pure distances by f, the frequency of that observation. And finally, step 4. Add all those multiplied values up and divide by the total number of observations, which is the sum of your frequencies, or sigma f. Now, while mean deviation relies on our absolute value magic trick, there is a totally different approach from our source material called standard deviation, and actually deals with negative numbers by squaring them. Like we discussed earlier, negative distances canceling out to 0 is a huge problem. Mean deviation solves it by just ignoring the minus sign entirely, but standard deviation solves it by squaring the distance, because, as we know, a negative times a negative is a positive. So I want to leave you with this final thought to ponder. If we stop ignoring negative signs and start squaring them instead, how might that change the way extreme outliers impact our understanding of the data's spread? Think about it for a second. Squaring a small distance of 2 just gives you 4, but squaring a massive outlier distance of 10, that gives you 100. Squaring acts like a giant magnifying glass on extreme values. So while mean deviation gives us a highly intuitive, direct average of distances using absolute values, other methods might pull our attention way more aggressively toward those distant outliers. It really makes you wonder which method paints the truest picture of your specific data, doesn't it?